Hi, this is continuation on our discussion on the nozzle and diffuser. And we come up with the unique equations for nozzle and diffuser after making some assumptions. So here's a quick recap. Our mass conservation equation will be mass flow rate coming in equal to mass flow rate coming out. So M1 dot is equal to M2 dot. For energy, we'll have this equation will have H1 plus half v1 square velocity square equal to h2 plus half v2 square. So h1 and h2 means the enthalpy of the inlet and outlet, and v1 is velocity coming in, v2 is velocity coming out. So knowing that, let's see if we can use this formula to help us solve this problem. So this problem, what is given? They said it's a steam, so we're going to use a steam table, right? So the pressure is given as 0.4 megapascal, and the temperature is 300 degrees Celsius. And then enter this nozzle, adiabatic. Well, if it's adiabatic, well, that means our heat transfer is equal to 0. Well, remember when we trying to come up with this equation, we already kind of made the assumption for heat transfer equal to 0, correct? So now, here I want to mention something. For any open device, in order to write down given, the best way to do, instead of writing like what I just did, it's actually better to draw. So I will draw a nozzle. Okay, so in that situation, I can put all of those here. I'm actually gonna move my nozzle to the left. So this is my nozzle. Because this is gonna be pressure P1, that's at the inlet, right? And then we'll also have this inlet temperature as 300. So to enter this adiabatic nozzle, Q is equal to 0 in a very low velocity. Well, when they mean very low velocity here, I have to tell you again, their mean velocity is equal to 0. Okay, so which means V1 inlet velocity, that's equal to 0. And it leaves at 0.2 megapascal. So here we're going to write down the pressure on this side. That's the beauty of drawing this sketch for open device. 0.2 megapascal, and the quality X is equal to 0.990%. They want to find exit velocity, which means find what? V2. Okay. So how do we solve a problem like this? Likely we're going to use this governing equation, right? Let's think about, in this equation we needed to know H1. So why don't we make that as our first step, finding H1. It's water, it's a steam that comes in. We have two properties already. We have pressure, 0.4. We also know the second property is 300 degrees. Knowing two property, we can find the third and the fourth means the other property. So here we want to find H1. So here we're going to go to our table. So 0.4 mega and 300. So which table do we go first? We don't know what phase, what region this belongs to, so I'm going to go to table A5, which is saturated pressure table. So let's see if I can take that out here. Okay, we're getting close. So table A5, this is 0.4 and 300. So 0.4 is mega, so that means 400 kilopascal. So let's go to 400 kilopascal, which is right here, right? 400 kilopascal, this is table A5. And what will be the saturated temperature? Is 143.61. Okay, so we found out that saturated temperature at 400 kilopascal is equal to 143.61 degrees Celsius. And here we have to make reasoning. Your given temperature T1 is 300 because this T1 is greater than Tsat. So we know that's going to be a superheated vapor. So if it's a superheated vapor that comes to this nozzle inlet, we're going to go to a different table. So which will be table A6, right? So we're going to go to table A6. Okay, so let's make a note. So we are going to, because of this, we are going to go to table A6 to find our H1. And it's at 0.4 megapascal. 0.4 megapascal in table A6. And it's at 300 degrees Celsius. So it's this particular row. And we want to read what? We want to read H. It's kind of difficult for me to use in this, but we'll do. We'll make it happen. So this is 300. It's this row. And then we're reading H. So will be the third column will be 3H1 will be equal to 3067.1. Okay. So that's going to be our kilojoule per kilogram for enthalpy comes in. Now we're going to go back to this equation, figure out H2. That's our second step. Find H2. H2, so that's outlet. They give us the pressure, they give us the quality. So we know state 2 is a mixture. Since it's a mixture, H2 is going to be equal to this equation, HF plus X HFG. They give us a pressure, so we're going to table A5, the pressure table. So going to table A5, find 0.2 megapascal. 0.2 megapascal, it is 200 kilopascal. Looks like we're here, so 200 kilopascal, right? So in here, we're going to find out what's going to be HF. So HF is going to be 504.71. 504.71. And HFG is going to be 2201.6 times quality 0.9. Okay, so let's do a quick calculation. See what do we get for our H2. So 2201.6 times 0.9 plus 504.71. And we have 2486.1 kilojoule per kilogram. That's our H2, our outlet enthalpy. Okay, so far we done getting the enthalpy ready, H1, H2. Now we go back to this governing equation, right? So that's our third step. H1 plus half V1 squared equal to H2 plus half V2 squared. That's energy conservation equation for nozzle. And H1, it's 3067.1 kilojoule per kilogram. And V1, it's low velocity, and which means V1 is equal to 0. So that's equal to 0. Then H2 is 2486.1 kilojoule per kilogram. Then we plus half V2 squared. Then we can find our velocity, right? V2. But before we go ahead and put into a calculator, I want you to pause for a second. Think about the unit. Unit for velocity. Velocity is meter per second. So you want to get meter per second. Is meter per second squared give us kilojoule per kilogram? That's something you want to investigate. So let's take a look at it. So here is our, with a post-it, we're going to figure it out. We know half mv squared, that's kinetic energy, right? If it's kinetic energy, that's going to have a unit of joule. So half, it's a number, has no unit, has no dimension. So mass is going to be kilogram. And velocity is meter per second squared. So basically, velocity squared or meter per second squared, that's equal to joule per kilogram. Okay? So here V squared is going to give us unit of joule per kilogram. However, in this equation, the rest of the term is in kilojoule per kilogram. So that's why we need to pause before we put into the calculator, right? We have to do what? We have to make sure this is going to be times 1,000, and this term will have to be times 1,000, okay, to find our V2. Okay, so let's go ahead and solve this. So half V2 squared is going to be equal to 3067.1 minus 2486.1. Gonna times that important 1,000. If we don't, the answer will be quite different, will be quite incorrect. Once you have this, your V2 will be equal to 2 times 3067.1 minus 2486.1 times, again, 1,000. Then we have to do a square root of that. Okay, with all of this down, your calculation, let's do it together. 3067.1 minus 2486.1, then times 2,000, then take our square root. Then we get 1078. Then you get your desirable unit as meter per second for velocity. So that's your V2. Okay, so quick recap on this problem. For this nozzle problem, we started with our energy conservation equation, and we realized we need to go find H1, H2. H1 is superheated vapor, so we find out its respective table. H2 is mixture. We find H2 using the formula. And then, most important thing is, realize whenever you solve any nozzle or diffuser problem, because likely your H from the table is in unit of kilojoule per kilogram. So make sure you're going to times 1,000, then put in your calculator. That will allow us to get our velocity in a unit of meter per second. So that's it. So I will see you next time. Maybe we will look at another example for nozzle diffuser. All right. Until then, bye now.